Hi, my name is Noor Hussaini and I'm a data scientist at TIBCO, and I'm here to teach you how to get the most out of using Team Studio. So today we're going to talk a little bit about gradient boosting in particular, but in this example I'm going to walk you through a gradient boosted trees classifier. So gradient boosting, and the principle behind it is that you're essentially using a lot of sort of weak learners, they call them, i.e. trees that aren't very fully formed to your data. But then you aggregate them in a way that they are continually learning from its predecessor. So the gradient boosting is essentially sequentially adding a predictor to an ensemble, and each one is then correcting the prediction from the previous. There's a few different ways to do this. I'll discuss the different approaches as to how the corrections can be implemented in Team Studio, and I'll walk you through the different parameters that you need to configure for a gradient boosting classification example, but it's the same for a regressor as well. So in this case we have a data set where we are trying to predict whether someone is likely or not to buy from us. We have some information on the customer, and we're doing the typical thing, which is splitting out our data into train and test, and then feeding that into a gradient boosting trees classifier. What we want to do is see if the parameters that we have implemented actually give us a pretty good model back or not. So I'm going to walk you through exactly all of the different parameters that you need to configure. The first, of course, is identifying the dependent column. So in this case, it was the has bought column. It was whether or not this customer had actually bought anything from us previously. And then the independent columns, again, you need to select at least one. In this case, I've just selected a few that I thought would be relevant to this modeling problem. So the loss function is what I highlighted in the beginning. This is where the way that each of the models that get added into the ensemble readjust themselves. So the default is logistic. You also have the known AdaBoost, also quite a popular algorithm, which is a little bit different to the gradient boosting technique, where it's, instead of fitting to the error like the gradient boosting does, it's fitting to the instance weights at every iteration. So it kind of starts with a guess of weights for every feature and then readjusts as it's going along. And the truncated hinge is even more involved. As always, the documentation for all of the operators is available if you just click this question mark, and that takes you to this page, the TIBCO's documentation on the operator itself. And in this case, there's even a link if you want to go into the more specific mathematics of the different algorithms and loss functions that you could choose. So importantly, the number of trees, maximum tree depth, and a couple of other of these, I'll talk you through the thinking behind them. So the number of trees is probably the most important, in that you're deciding how big your model should get. If you increase the number of trees, your model improves in terms of its accuracy, but you are trading off optimization in terms of time. So your runtime would obviously increase, and it increases linearly because every time you're adding on a new tree, it has to go through that configuration. So there's that trade-off of increasing the accuracy, but also minimizing the performance time that usually is the challenge with ensemble methods in general, but in particular this one as well. The maximum tree depth refers to how big of a tree you can create with your data set. Now again, it says maximum, so if in the particular learner that the model is optimizing on, if it does actually finish before the maximum tree depth, in this case this is 3, so this is 3 from the root node, then it will just conclude and then move on to making the new learner. The minimum node split size refers to the minimum number of members that are required within each of the nodes before a split can actually be performed. Bagging rates refers to how much of the data is actually sent to train each of the learners. So if we're sending a certain amount of data, each of the different learners see, in this case, the default, of course, is also half. So each of the learners is seeing half of the data that is being sent to them, and that in itself helps to stop overfitting. The shrinkage refers to the weight given to every single of the trees. And then the fraction of data for training refers to the amount of the data that is sent to create this model and how much is left as a holdout set. So this is how the trees learn and assess how well they are performing. That fraction is what you set here. Return the optimal number of trees. You can set that to yes. This is measured against the validation set. So this is measured against whatever fraction is left over here. And some more other, and of course there are other parameters, but like I said, that those are probably the most important when it comes to optimizing your gradient boosting classifier. And in this case, in this workflow, you can see the output of the model looks as such. So you get a summary of the different parameters and what it looks like. And an interesting part is here you can actually see the deviance of the learners as we're going along. So each tree that gets added on, you can see that the validation is consequentially dropping. And actually you can view this in the deviance chart here, where you can see that the training and validation is continually dropping. And also, as with other trees, you get variable importance ranking, and in this case you have the importance shown as the absolute value. So that is essentially ranking what of our features is most important, most informative to the model. That's gradient boosting. Just to show you quickly the regressor model, even though this is not a regression problem, and that the parameters are similar. So you'd have to specify the dependent column, the independent column, choose a loss function that's slightly different to the classification problem, and again, typical to trees and ensemble methods, you have to specify the number of trees, maximum depth, etc.